Okay, welcome everybody. So this is going to be a very short presentation. Actually, it's going to be kind of like a smaller, how do you call it? Yeah, kind of lecture. I mean, it's not a workshop, yeah. So it's a small workshop about training neural networks with ForneyLab. So I guess you all know like this, the idea of neural network, and I also imagine that many of you have already worked with ForneyLab. So I decided to show it is possible to train neural networks with ForneyLab with the recent features in the ForneyLab regarding this nonlinear node. So we are going to use the nonlinear node of ForneyLab to train neural networks. Okay, so this is an alternative cover we have here. So by the way, if you have any question, please interrupt me. Okay, so okay, let's continue. Okay, today's agenda is I'm going to talk about the motivation. Why do we want to train a neural network with ForneyLab? Because we have other tools, right? Like we have Flux in Julia, and in Python we have PyTorch and also TensorFlow. So why do we want to use ForneyLab to train neural networks? And then I'll talk a little bit about training neural network in a nutshell. Then we will dive into details of training neural networks with the nonlinear node of ForneyLab. Okay, and finally, I'm going to show you a a Jupyter notebook about the implementation, and but this is kind of like an ad hoc implementation. Okay, so we will talk about the drawbacks of this method, so you can ask your questions as well. And let's get started. So why do we want to train neural network with ForneyLab? Because we have Flux, but the thing is that Flux is not a probabilistic programming package, so it is not directly possible to train the probabilistic models together with the neural networks. I mean, you can build that. I mean, by introducing your own functions, right? I mean, by designing like the message passing algorithms on Flux, this you can do. But we have ForneyLab specialized for this purpose. And it is maybe easier to try to basically compose Flux with ForneyLab directly so that ForneyLab can handle this probabilistic programming part, like the Bayesian inference part, and Flux can handle the deep learning, the neural network training part. But this is not that easy. I mean, for some reason, ForneyLab throws errors when you try to like combine Flux with ForneyLab, and also like the influence of like neural network and the probabilistic models differ a little bit, which also impedes using deep learning tools with probabilistic models. So, but it would be really nice, right? I mean, bringing the best of neural networks and Forney-style factor graphs for different purposes. For example, here I try to visualize a simple model. So in this model, this is like a Kalman filter, right? The upper layer. So this parallel layer, like this horizontal one, it is like a classical Kalman filter. So we basically model the conditional distribution between the time steps. These time steps are like the variables are hidden, and from hidden variable to observation, we want to put a neural network maybe to model some structured and high dimensional data. For example, consider video, right? I mean, let's say that we have video, and here we have these observations from video, right? I mean, all these like these are each of these observations are frames from video, and we would like to learn maybe a lower dimensional representation of video. And in this video, we know that it is like a consecutive frames coming to our eye, and maybe this video, the whole these hidden variables are living in a lower dimension, and we would like to extract this information. Okay, so this kind of model, for this kind of models, we may want to use neural networks. So how do we train neural networks? So this I guess you all know, but I would like to talk a little bit about it. So basically, we try to maximize log evidence, right? Given that X is the input and y is output, and the w is represents the weight. And we would like to maximize this log evidence with respect to weights. I mean, the weights basically becomes the parameters of a function, and function here neural network. So this is maximum likelihood training of a neural network up until regularization. So if you just ignore the regularization part here, this is maximum likelihood learning, right? And many of the times we see that it is possible to add regularizations here. For example, this is one type of regularization. So this regularization is known as L2 regularization. Okay, this basically says, if you check here, okay, we would like to maximize the log evidence right here. So we have this regularization with minus, and basically this punishes these W's, like the weights with a large norm. Okay, so if the norm of the W increases, then we basically punish this objective function. So we basically tell here our neural network that, okay, I would like to learn these parameters W, basically the weights of neural network, to basically model the observations, right? But I also want to keep these weights closer to 0. Okay, so and how do I encode this information? Is basically by regularization. So this is the most often the way we train the neural network. But actually this comes from prior over the weights. So if you just write this objective with the likelihood and the prior, and maximizing this objective with respect to W, you basically reach the same regularization. Okay, this I show here. So it is basically training a maximum posteriori with a maximum posteriori objective. Training a neural network with a maximum posteriori objective basically refers to putting a prior on the weights of neural network. So here we are going to do something similar with ForneyLab. So in ForneyLab now, I mean, we have a bunch of implementations for nonlinear node. So unstandard Kalman filter is possible with nonlinear node. Extended Kalman filter is possible with nonlinear node, and also Laplace approximation is possible with nonlinear node. So how do we do this? Basically, we basically collect the messages, right, in the factor graph. So for example, if you check the messages here, so this part, this second part is basically the prior, right, for the W, and the first part of the objective function is basically the message, the information coming from the likelihood node, right? And the way Laplace approximation works is the following. So basically we try to approximate the actual posterior with a Gaussian distribution. And the way we do it is, okay, multiplication of the messages, multiplication of the messages gives us this objective, right? I mean, this posterior is proportional to multiplication of the messages. And if you find the mode of this objective function, we know that in Gaussian distribution, the mean of Gaussian distribution coincides with the mode of Gaussian distribution. So basically finding the mode refers to finding the mean for approximating Gaussian. And after that, by using this curvature information, by evaluating the Hessian of the objective function at this mode, refers to evaluating kind of the covariance function for this approximating normal distribution, right? So we are not interested in the curvature here, like the variance of the posterior in this specific example. We will directly use the mode seeking feature of Laplace approximation, and Laplace approximation in ForneyLab is automated already. So the way we do it is so basically we initialize this W0. So we initialize with learning with the W0, right? And we initialize it with the mean of the prior. So, and then we have a system that adaptively sets the learning rate here. And then we use this classic gradient ascent, right, to maximize this objective. So at every iteration, we evaluate the gradient of the objective, and basically we follow this gradient by setting the learning rate adaptively. So this is the way we automated Laplace approximation in ForneyLab. So, but this has been designed especially for low-dimensional problems, and it works really, really nice in low-dimensional problems. But in neural networks, we will deal with high-dimensional problems. I mean, it's for example, I'm going to show you in an experiment, and we will try to learn basically the weights of neural network, and the weights of the neural networks refer to evaluating a Laplace approximation for 20 dimensions. So 20 dimensions for neural network is something like a low dimensional, but for our implementation, it's kind of a high dimension. So we basically implemented an adaptive gradient ascent method, but this is quite primitive. So it would be nice to build some other optimizers for this kind of purposes. But we will see that it is still possible to train a neural network even with this simple gradient ascent optimizer. Okay. Okay. Let me continue. So what we are going to do is, okay, as I showed you here, in Laplace approximation, it is automated in the way that we initialize weights with the priors of the W, right? So normally, it would be nice to put a zero mean normal distribution prior on the weights, but if we do this, then the automated Laplace approximation will initialize this W with the vector of zeros, and in the vector of zeros, the neural network is most often in a stationary point. What I mean with stationary point is that at this point the gradient is basically zero, so there will be no learning in this setting. So we would like to avoid this, and in order to avoid this, what I'm going to do, I'm going to initialize this W0, this prior with something else, right? I mean, it's not going to be zero, but it's going to be something very small. And after that, at each iteration, the Laplace approximation will find us some good values for W's. But as I told you, this system, like the gradient ascent, is automated for lower dimensions. And to be honest, it is not possible to learn some good W values with just one epoch over the data set. So what I mean with the epoch over data set, so we call passing. Okay, so we basically pass through the data set several times in deep learning most often, and this is called epoch. Each of them, like passing through the data set once is called one epoch, and we need several epochs to train our Laplace approximation. And each time I'm going to do the following. I'm going to basically update the prior over the weights with the priors from the previous W values. So, and then I also set the covariance to some value, and this covariance will basically determine how much I allow these weights to differ from the previous weights. So basically, this system here, what I'm going to do is I'm going to start with some initial W values, like the weight values, and at each Laplace approximation, we are gonna learn some parameter values, new parameter values, and in the next epoch, I'm gonna change the prior with the weights from the previous optimization. And basically by doing this, I'm saying our system that, okay, you are free to learn these weights to explain the data, the observation plausibly, but I do not want you to move away a lot from the previous weights. Okay, so this is what we are going to do with ForneyLab.
Okay, can I ask a question?
Yes, sure, definitely.
Yeah, maybe I just missed that, but just to be clear, so what are the inputs and outputs of this neural network?
Okay, the inputs are the X, right? So the X, okay, I basically I showed here, but X is the input of this neural network. So we have some features for the data, right? And we have some outputs, like the classes for each data instance.
Yeah.
So this is the output. And we have these weights we would like to learn, right? These are the parameters of this function. So this is the input, output, and
no,
parameters.
I mean like an example or something. What did you use or?
Yeah, I'm coming there. I'm coming there.
Okay.
So this is the example, okay?
Okay.
Okay, so this maybe it is actually easier to go with an example here. So in this example, I'm gonna implement a neural network with ForneyLab to train this neural network for this data set. So in this data set, we have the features for each data instance, right? So what are the features here? The feature for one data instance is basically the coordinate for this instance. For example, here, if we check this one, maybe this one is easier, okay? So this one, the feature of this instance is -2 and -4. So basically the coordinates of this instance, and the output is going to be basically red, right? I mean, we have either red dots here or blue dots, and we would like to classify these instances. So this is the input output for this neural network. So let me show you. Okay. Let me show you the implementation. Maybe I'm passing too fast. If you have any questions, please do not hesitate to ask your questions, guys.
I have a question. I'm kind of unclear on this. So
Okay.
the vector graph or the nonlinear vector graph, it doesn't observe the ground truth, right? So you're only giving it the features.
I'm giving it features and also classes, right? This is a classical neural network training. So basically, if you check here, so we basically have this training data set, right?
Yeah.
So, and in this training data set, we have the inputs for each instance, and we have output, basically the class of the instances. So we basically feed the system with inputs and outputs, and we want to try to learn W's here.
Okay. So the network during training does observe the ground truth.
Yes. You need this. I mean, otherwise there wouldn't be any learning, right?
Yeah, unsupervised learning, right?
Yeah, but but this is I see your point, but this is supervised learning, yeah.
Okay.
I mean, this example is supervised learning, but you can also implement something similar with unsupervised learning. I mean, this is just a simple toy example.
Yeah, obviously. I was just curious because that would be like the big breakthrough, right, in in neural networks, if you wouldn't need supervised or supervised data anymore. So if you could use unlabeled data.
We use labeled data. It's going to be way more clear with the example I'm going to show you here. Okay, so this is as I told you, this is the data set, right, generated from the from Turing's website. So in Turing's website, they also show a neural network training with their, I think, Hamiltonian Monte Carlo inference engine, and this is the example they use. So far, this is just basically having the splitting the data with the features and the class information. Okay, so we are going to build our factor graph with ForneyLab, and basically we have the weights, as I told you, and we put a Gaussian prior on the weights here, and for the mean and the covariance of this prior, we put placeholder. The reason is that at each epoch we are going to update this mean. Okay, so that's the reason why we put this placeholder. We will start with some initial weight values, and at each epoch, after the Laplace approximation downweight optimization, we are going to change the prior parameters. And then we have these weights here. So we basically, yes.
Can you hear me?
Yes, I hear you. Well,
okay. Can I ask a quick question still
sure.
Before you proceed with this? So I'm assuming now that this is a neural network with a weight matrix that is 2 by 1.
I'm going to give you the information about this neural network structure in a minute. It's not
because
too wide bound. No, it's not too wide.
Yeah, my question would be that if you have a weight matrix that that maps, so your input space is 2-dimensional, and if you have a hidden layer that's, for instance, larger, for instance, 3-dimensional, then you'll have a weight matrix 2 by 3. Do you then do the Laplace approximation for every column of the of the weight matrix, such that you get 3 Laplace approximations, vector, or do you reshape that weight matrix into a single vector and then do the Laplace approximation on that single vector?
This is a nice question. So what I'm going to do is the following. So for all the weights, I'm basically concatenating them, right? Because in neural network, what we have these matrices, biases, and biases, and it goes like that, right? So instead of doing this, what we are going to do is we are going to put every weight value into a large vector. So here, for example, you see that I'm putting a Gaussian prior on the weights, which is 20-dimensional, right? And in the next step, I have these two functions here. So the first function is unpack. So in unpack, I'm feeding it with this large vector, 20-dimensional vector, and this function basically split this large vector into weights, into matrices and biases. So for example, here I give this 20 dimension, and then it takes the first 6 dimensions and makes it a 3 by 2 dimensional matrix. And then it takes from 7 to 9 these 3 dimensions here to create the bias. So it goes like that. And then I learned this Laplace over this large vector. Okay.
Do you think it makes sense to have multiple Laplace approximations? Because I can imagine the weights might be I find it hard to put my finger on this, but is it possible that the weight matrix is multimodal? Therefore, it would be good to have multiple.
That's nice. That would be really a better way to train this neural network. I definitely see your point. So you say that there are probably more than one mode, and it might be a good idea to initialize different Laplace approximators, maybe with different initial weight values, right? And each of them will converge to something else, and then we can pick one among them. Is what you are asking. That would be a better implementation, I think. I agree. But even this one with one Laplace, it works pretty satisfactorily. That's what I can say.
Well, I look forward to see that. Thanks,
Yeah, sure. But as I told you, this is kind of like an ad hoc method. So it is not like a very scientific in the sense that normally the best way to train a neural network with Laplace approximation would be the following. So we would basically put a zero mean, maybe unit variable, I don't know, like it depends on the constraint, but with some covariance here, but putting a zero mean Gaussian as prior on the weights, and then initializing the gradient ascent with different weight values and training it with good optimizers. That would be the best way to train a neural network with Laplace approximation. However, as I told you, the automated Laplace approximation in ForneyLab starts initialize these weight values with the prior over them. So if we put the zero mean prior on the weights, it will initialize the weights with zeros, and the zeros with and then we get stuck in a stationary point, and there will be no learning taking place because the gradient in these values is basically zero. So because of that reason, I'm gonna initialize it with something else. And the other thing is that since our optimizer is automated for low dimensions, in high dimensions, it is not enough to learn very good parameters. So instead of this, what I'm going to do is I'm going to at each epoch, I'm going to update the prior with the previous weight values so that it can like move away a little bit from these previous Laplace and learn these good weights to discriminate the data set. Okay. Any other questions, or I'll continue with describing the.
I have more like a programming Julia related question. So what is the type of X-train? Is it the matrix or it's like a vector of vectors?
Vector of vectors. So you can, let's see.
Because I mean, I just see that you use X-train N, right? And you like.
Okay, you see, right?
Okay, so it's fine. Okay. Because I'm like, if it would be a matrix, I made this mistake as well. You don't use colon, right? In
no. I see your point.
Just to make sure, I mean, but then it's fine.
Yeah. Maybe it is good to show the train and data, this feature and output of the data, because so you see that these are the features we are going to use, and each vector here refers to one feature, for one data instance. For example, this is the feature for one data instance, right? This is the feature for the second instance, third instance, it goes like that. And this is the output. So we basically say, okay, this one basically refers to class 0. The second one refers to class 1. Goes like that. Okay. So I'm gonna just cut them to. No, I don't have to. But okay, it's anyway. So let's continue with the model. Okay. So as I told you, we define a prior over the weights here with placeholders for mean and covariance matrix, and we have n observations. So n is basically 80 here. So we have 80 data instances, and for each data instance, we instantiate a neural network here, okay, with the given features for this data instance, okay. So this data instance is the input, right? The first input, and these are basically vector values. So we know these values. These are the features, right? And we have this W here. So W is basically the argument for this function. And for each data instance, we create different function to avoid the loops. So this is something you have to keep in mind, that ForneyLab doesn't allow loops with nonlinear node. So in order to avoid it, I basically create different functions for each data instance. So it's like a func1 for the first instance, func2 for the second instance, and each func has its own feature set as the input, okay, and there is another argument which is W, and this argument basically stands for the weights. So next time you see that I have another variable Zn, okay, which takes the weights as the input, okay, but these weights shared among data instances, which is a global random variable defined here, okay? But the function basically changes for every data instance. The reason is that the input changes for every data instance, right? And this random variable refers to the parameters of Bernoulli distribution. And our likelihood will be Bernoulli distribution. The reason is that it is basically like 0-1 classification, right? So the output will be either 0 or 1. So we basically model the parameter of the Bernoulli and the output will be Bernoulli, okay? And we basically put a placeholder for output as well. We will feed it with data. Okay, any question?
Semih, do you... Oh, hi?
Yes.
Oh, yeah. Semih, do you really need that eval statement? Couldn't you use an inline function, x, and then hyphen right arrow to and then forward x? No?
No, it's like the way how ForneyLab handles this lambda functions, it's impossible.
Aren't they separate objects, the lambda function?
So what we'll do, like when ForneyLab will generate like an algorithm, you will just get this sharp name of the function, of a lambda function, but not the function itself. And it will it basically couldn't find it if you use lambda for G.
Okay. Damn. Okay, thanks.
As I understand, it's a hack. So yeah, basically you're right, Wouter, but it should be like
yeah.
But it doesn't work.
Too bad. Thanks.
Yeah, exactly. This is kind of like a hack you have to do to avoid the errors.
No, I understand.
Okay.
I was just bummed.
Any other questions? Is this clear for everybody? Okay, so maybe we can also take a look at the neural network structure again. So as I told you, for each data instance, we instantiate a neural network here. So this neural network is basically have the following shape. So it takes this two-dimensional input for each instance, right? And then maps it to three-dimension. Also, we have this bias term here. Then we basically put it into an activation function, which is hyperbolic tangent defined here. Okay, so I defined the hyperbolic tangent here. So this is from the input to the first hidden layer. And I'm doing something similar for the second layer, this time from 3-dimension to 2-dimension, and we have the bias term for that as well. Again, we use this hyperbolic tangent for the activation function, okay? And lastly, we map from this second hidden layer to the parameter of Bernoulli with this sigmoid function, because sigmoid function takes values from 0 to 1, okay? So this is the neural network structure. Okay, so this is the neural network structure. This is the model, and we basically ask ForneyLab to build algorithm for us. Okay, and then if we check this algorithm, you will see that it is basically okay. There are a bunch of messages here, right? But all these messages actually designed to collect the information from the likelihood, because we have A2 of them, right? And we have a bunch of like these equalities, etc. They are getting multiplied and they travel in the graph. And the resulting marginal will be multiplication of message 1 and message 240. So message 1 basically stands for the prior of the weight. And message 240 is all this information collected from the likelihood. We have like bunch of 80 observations, and from all these observations, we basically collect information, right? Okay, so far so good. We have the algorithm. Okay, let's train the neural network. So I basically, as I told you, start not with vectors of zeros, but some small values. Okay, so I randomly initialize it and divide it by 10. This is something, a trick that is being used in neural networks, because you have to initialize these neural network weights with some small values, but so that there will be like some gradient values, because if you take them like a high, then the gradients will be very close to zero and there will be no learning. But if you make them really small, then there will be no difference between the layers and between the neurons, and there will be symmetry, so there will be no learning as well. So it is often good to start with something like randomly initialize it with Gaussian and dividing by 10, so it's going to be like 0.1, 0.05, this kind of values will your initial weight take. And as I told you, we start with and I put this variance here is basically unit variance. Okay, but you can change it, and changing this will determine your regularization coefficient. Okay. Okay. So we basically take the step at each iteration. So as I told you, this is iteration. This is basically the epoch. So at each iteration or at each epoch, we pass over the data once, and we do it 20 times. And each time our Laplace approximation finds some good values, but by changing the prior here, the mean of the prior here with the previous weights, we basically tell our neural networks, our optimizer, that okay, now you found this point, but by putting the prior over this point, I want you to find another point that is close to this one, but explains this data set better. And at each iteration, it gets updated. So you see, right? I mean, it doesn't change a lot, but it basically fits better to data. So if you do it like a lot, so I basically use 20 iterations, but if you do it like 200 or 2000 times, it's going to be overtraining, and this is overfitting, right? It's going to overfit. So this is something we have to be careful with the neural networks. So far, do you have any questions?
So this procedure you use, like if re-updating your prior, I mean, I totally understand it, but just as a question, can it be an issue? Because indeed, you like restrict your algorithm to move a lot, right? It always moves on in this region. Can it be an issue?
It basically refers to the following. You remember this part? I explained the neural network training, right? Mm-hmm. So if you do not put a regularization here, you basically do maximum likelihood learning. So what I'm doing is something similar. So I let these W's to move away from zero. So if you remove this regularization, the W doesn't have this constraint on them, and it can use purely the gradient over the log evidence to explain the data. So this is something what we are doing. But at each iteration, we basically say that, okay, you are free to go beyond zero, but I do not want you to go a lot from the previous iteration. Yes. So it's basically what we are doing is something between maximum likelihood and maximum a posteriori. So neither of them. I mean, it's not like a pure maximum likelihood learning, because we still have some restrictions on W, but it is not pure maximum a posteriori as well.
Yes.
Okay, and then let's see the results. Okay, this is how neural network basically make the classification over the whole terrain. Okay, I'm not showing these data instances yet. I'm going to show them. It is just to show that if we give a value from here, the neural network will classify it as 0. If I give here, it's going to be classified as 0. But if I give here or here in this region, the neural network will classify it as 1. Okay, this is what our neural network has learned. And let's see them with the data instances. So these curves here, I mean, there are a bunch of them, right? So basically, I use the contour feature of plots.jl, but I didn't like the plots a lot. But yeah, this basically shows us the discrimination border. So these borders are discriminating zeros from ones. And here, these reds and blues, these dots, they are our training instances. And I'm going to use these yellow star points to test the prediction power of our system. And you see that it is like, if we give this as the input, -4, -3, which refers to this yellow. By the way, you see my cursor, right? I'm using it a lot, but
okay. We see your cursor.
Okay, cool. So this yellow instance, our neural network classified it as 1, as expected, because we showed it here. So this region is 1. And for this point, 4 -4, which refers to that yellow star, it is classified as 0. So for it is this one is classified as 1. Here, this refers to -1, 3. This is classified as 0. It is still beyond this border of 1, so it is 0. If we check this one, which is on the border, and it is 0 and 3.4. I mean, this is the point. This is the instance with the coordinates 0 and 3.4. This is on the border. This is classified as 0.5. So our neural network is not sure about the class of this data instance. So this is the prediction for some test data. So these are the results for my presentation. So let me make some caveats about this approach. As I told you, the motivation behind training a neural network with ForneyLab is that it's sometimes really hard to combine this flux with ForneyLab. I mean, it is possible, by the way, right now, to do it with reactive message passing. So because I tried it and it is possible. It is possible. It is just you have to use not the automatic differentiation tool of flux, but you have to use this reverse diff.jl to train the neural network. But it is possible with reactive message passing right now. But it is not possible. At least this is what I saw with ForneyLab. I tried it with ForneyLab. I got some errors. So instead of this, if you want to really incorporate the neural networks into probabilistic graphical models and Forney-style factor graphs, and we want to learn maybe these high-dimensional observations with neural networks and some other part with the classical probabilistic graphical models, it might be a good idea to use this kind of idea. Caveat is the following. In Laplace approximation, this optimizer is automated, and automated having low dimensional problems in mind. And also like having in mind that we are going to use poorly done for like not neural network type structures, but something way more similar, maybe like classical linear regression, or maybe Bayesian logistic regression, right? So for these purposes, we automated the system. So it's very like primitive. It might be a good idea to implement different optimizers beyond like gradient ascent, so that we can train a neural network with this approach. Okay, so if you really need to use neural networks, like a poor neural networks, go with flux, of course. But if you want to incorporate neural networks with maybe Bayesian inference and probabilistic models, then you may want to use this approach. Okay, so this is it from my side. Any questions?
I have a question, Semih.
Okay.
So in most convolutional neural networks, like the kernels themselves are relatively small dimensionally. It's just that there's a lot of them, right? So they can, it's not that uncommon to have a kernel of 5 by 5. It's just that you have multiple 5 by 5 kernels. Is it, you're now, with the way it's implemented, or the way I understood it at least, the weights of different layers are not independent from each other, right? So you have this covariance matrix that spans every weight in the system.
This is true. This is true. They are not independent. Yes.
Have you
yes.
considered making these layers independent and implicitly using the gradient descent to incorporate the dependence between the layers? Because that's what they're doing now, right?
So here is the thing. Yes, they are dependent according to the model specification, but what I do here, you see, right, each time I basically update this variance with unit variance, and this here, I basically impose this information that they are kind of like independent from each other. So in that regard, I haven't used this idea of like correlation between the weights. So here's in this implementation, they are still they do not have this correlation. The problem with correlated weights is that, as I told you, this Laplace approximation is like designed really like for small problems, and relatively remind some convex objectives. I mean, it doesn't have to be convex, but it's in neural network they are really like non-convex. And if I evaluate the variance terms after the Laplace approximation, I saw some problems. The problems are related to the positive definiteness. So
okay.
So that causes problem. That causes problem with the Laplace approximation. So I guess, I mean, it can be because of two reasons. The first reason is Laplace itself. So as I told you, this neural network lies on this manifold, which is very non-convex. So maybe we find these stationary points with really not positive definite covariances, not positive definite curvatures. That is possible. This is and this is the drawback of Laplace approximation. Or it can be either because of our implementation of gradient ascent. That is the second possibility. So I don't know this yet, but we get some problems when we want to use this covariance information and correlation information. Otherwise, I wouldn't resort to maximum likelihood, maximum a posteriori optimization. I would directly learn the posterior over the weights, which would give me Bayesian inference, right? Bayesian neural network. But no, we have some problems with that, and I don't know the source of the problem.
Do you think it's fixable? Do you think there is a solution to this? Let me put it like that.
So the thing is that it has to be investigated first. I mean, what is the reason we see this problem? Is it because of the Laplace, or is it because of the gradient ascent we implemented? So if it is the gradient ascent we implemented, it is easily fixable, right? I mean, we can implement another optimizer for like neural network type of stuff that uses maybe momentum information or other optimizers like Adam and Adegrat, some stuff like that, right? And this is something we can overcome. But if it is because of Laplace approximation, then we have to implement another inference engine. Maybe with Markov chain Monte Carlo, maybe with HMC, Hamiltonian Monte Carlo, I don't know. But this second issue is harder to solve.
Yeah.
So we have to first understand what is the cause of the problem.
Thank you. Looks really cool, by the way.
Yeah, thanks. Okay. Any other question? Okay.
I had a question, Sam.
Yes.
So first, just to check whether I understood it correctly, suppose I want to do regression instead of classification, so neural network regression. Instead of the Bernoulli likelihood, I could put in a Gaussian normal.
Yes, definitely.
Univariate normal.
Yes.
Then suppose that likelihood, that Gaussian likelihood, has an unknown noise parameter or unknown variance parameter.
Okay.
And suppose I would like to simultaneously estimate that unknown variance parameter for the regression. Would I then update that once every epoch, or do you think I should update that every time I'm doing an update to the weights, or maybe even less often? What do you think I should do there?
Okay, this is a nice question. So let me think of it just a second.
Sure, take your time.
So normally what would be nice to do is, so the way we learn neural network is we learn it with gradient ascent, right? I mean, or gradient descent if you minimize the negative logarithms anyway. So it's basically like a stochastic gradient optimization. And in Bayesian inference, we know that basically these closed form updates of, for example, VMP refers to gradients of free energy. But we do it in a way that we basically set the step size to 1, which refers to coordinate ascent variational inference. So setting
it's coordinate ascent because you're only updating parts of the gradient, namely those parameters of a particular recognition factors, not all parameters at the same time.
Yes,
but
yes.
It's the step size, I think, is 1 because you're solving the gradient with respect to those parameters analytically. You can just set the derivative to 0 for those specific parameters, then you obtain that result.
Exactly. So my answer would be the following. So instead of setting the step sizes to 1 for variational inference, maybe like setting it to somewhere between 0 and 1, especially like with a decreasing order, right, for this stochastic optimization. These weights and the variational parameters has to be updated simultaneously. So it shouldn't be like in an alternating manner, because the variational message passing is an alternating optimization method, right? As you described. So we basically update one, and then by fixing it, we update the other one. Then we update the other one. But in gradient descent, once we start with gradient descent, then it is better to keep everything gradient descent. And in gradient descent, we update all the parameters simultaneously. So I think these weights and the variational parameters has to be updated simultaneously. So that is
the decreasing step size.
Yeah, with decreasing step size, because each time.
Okay.
So in the beginning, probably you need more step size, right? I mean, to learn first steps, and then as your system getting closer to these stationary points, you shouldn't take that much of step, because otherwise you will move away from these stationary points. So you have to decrease the step size. So that would be my answer. I don't know if this is an answer to your question, But
no, I think that's definitely a way to update the variance parameter along with the weights.
yes.
And then your reasoning makes sense. But the other ideas that come to mind is perhaps that, so the variance of the likelihood represent, so if you have some deterministic, so in linear regression, you observe a bunch of outputs and you span a line to that, and your variance parameter of your likelihood represents how much each of your outputs deviates from that line.
Yes.
And so perhaps I can also imagine that you would go through the data once, update all of the weights. That essentially gives you a nonlinear regression function. And you compute how much every output differs from your nonlinear regression function. And then you do a single update to that variance parameter based on the total set of residuals. Then once you go through the entire data, updating the weights, and then once you're done, then you do another. That's something that came to mind. But the procedure you sketch is also seems very reasonable.
The thing is that yours, I think yours is yours fit better to ForneyLab, in the sense that ForneyLab is designed for this kind of alternating optimization, right? And I think it has a potential that it may work. It may work. So my answer was like mostly about like how to do it theoretically, but from practical point of view, yours makes more sense. And also I think it might be the true way to do that. I mean, it is possible. And here we shouldn't forget that I'm also using like ad hoc method to train this neural network, right? So
yeah. No, but I mean, it looks it looks amazing. It looks very feasible. Like I kind of want to get started on training neural networks.
yeah, thanks. Okay. Any? Yeah, thanks, Walter. If there is no other question, I am gonna stop sharing my screen.
I have one more question. It's Philip, by the way. My computer crashed.
Okay, yeah, go ahead.
Have you compared this to just plain old gradient descent?
No. But here is the thing: gradient descent, like a regular gradient descent, has the potential to work. Okay, probably going to work with a similar performance, I guess, because this is something simple problem, right? I mean, this problem. Yeah. This problem is even very simple for Laplace approximation, at least with the ad hoc methods I'm applying, like all these tricks. So yeah. I think it would be better to test them with different and harder data sets, because for this one it takes like, I don't know, maybe like 10 seconds or 15 seconds for my algorithm to learn, right? I mean, this ForneyLab to learn 15 seconds. And it's pretty satisfactory, the results. So I can imagine that gradient descent would do in the same way. Because in the internals of Laplace approximation, we are using this gradient ascent. The only difference is that we just update these step sizes here. You see these step sizes at each iteration adaptively. Yeah. So maybe this adaptive setting of the step size is not a good idea for this problem. That's also possible. So maybe gradient ascent, pure gradient ascent, is a better way. So I don't know. I mean, yeah, I didn't. Short answer is I didn't.
Yeah, it would be interesting if you could expand this to a dimensionality of 300, because that already gives you the possibility to run data sets like MNIST to see if it can actually do handwriting recognition.
Yeah. No. I see your motivation. Actually, I thought that maybe I can show a variational autoencoder, because I think variational autoencoder can also be possible with this method. I thought that maybe I can show it on MNIST dataset, But then, to be honest, I didn't have too much of time.
Yeah.
So I just came with this one.
Yeah, but downscaling MNIST that much would also, because MNIST is like, what is that, 26 by 26 pixels or something, if I remember correctly. And
Yeah.
downscaling that to, what was it, 5 by 4 might be a bit much.
Make factor of it easier.
It could work. That could actually work.
Yeah. It is. It is hard actually to train on MNIST, but yeah, it would be nice to just see. I can imagine that probably it would be really hard to train this neural network on MNIST with this with a batch manner, but online can be possible. Online can be possible because
because MNIST has also been used with hidden Markov models to estimate what class the letter belonged to. So like there's a lot of research, or a lot of research has been done with the data set. So it's also a nice comparison to be made.
I see. So you are imagining something like, okay, just a second. Okay, my computer doesn't react now. Okay, now. So you say that, okay, maybe something like this, right? So instead of these normal distributions here, maybe we can put a categorical, right? And then putting some neural network here and the output as MNIST, we can build some kind of hidden Markov model. And
for example.
Yeah, would be interesting.
So what I know is that one of the first attempts with MNIST was to sum all the columns of every image. And then I don't exactly remember the model they used, but they used some state space model or something. Or I don't remember what they used. It's so long ago that I read this. But they used some model to then classify based on the sum of the columns of these MNIST data images. Which already reduce the dimensionality enormously, right? All of a sudden you get the square of the dimensionality, and that would be that might actually be a possibility, because then if you have a fully connected layer of 20 by 20 weight.
You can also map the each image down by PCA.
Yeah, that's what Bart said as well. I thought everybody heard.
Oh, sorry. I didn't. That's what Bart students are doing at the moment in their final assignment.
But I'm quite suspicious if Laplace approximation and our optimizer would work in that case. Yeah, it has to be checked, right? I mean, but the best way to overcome these problems is to build a proper optimizer in ForneyLab and doing this stuff, because it's just the aim here in this presentation just to show that it is possible, right? So basically, by replacing this optimizer inside the ForneyLab, it must be possible to learn neural networks. So, and this is very ad hoc method. Again, I'm warning everybody. So it's maybe it is good idea for like small problems, and but we have to have in mind that this is kind of ad hoc. But yeah, I agree. It would be interesting to test with MNIST and all this stuff. Okay. Just a second. Okay, I guess you see me now. Okay, nice. Any other questions? If not, then
I will stop the recording.
Okay.